So good morning, everyone. Thanks again for all coming. We really appreciate you guys being as interested as us in the topic. So my name is Natalie Douglas, and I'm working at the City of Nelson here as the Embodied Carbon Pilot Coordinator and Climate Change Planning Assistant. I've been really lucky to be able to work with this awesome team that consists of Michelle DeLuca from 3 West Building Energy Consultants and Javaria Ahmed and Chris Magwood from Builders for Climate Action. As a group of unabashed building and emission reduction nerds, we feel incredibly grateful to be helping Nelson and Castlegar come into the forefront of the green building discussion and finally get the chance to engage with some stakeholders. So on a more practical note, if you have any questions at all, just throw them in the chat and I'll be compiling those and posing them to Chris at the end of the presentation. And before I pass things over to Chris, I do want to give you a sense of how Nelson got here and how this project is set up. This next slide. So it actually all started with Sam Ellison, the senior building inspector here at the City of Nelson. And he began wondering whether we were missing something in the green building conversation and energy efficiency conversation. He wanted to get some data on how high step code homes were performing in terms of their overall emission contributions when the embodied carbon was accounted for. He connected with a local energy advisor, Michelle DeLuca, who also had similar interests and access to a beta embodied carbon calculator tool created by Builders for Climate Action. This then led to a small 3-house study born in late 2020 and completed in early 2021. The study found that further research did indeed need to be done to get more data on the local context, offer tools to folks in the building community here, and identify key materials to focus our reduction efforts on. So Sam and the then climate change coordinator, Kate Letizia, promptly sought out funding from Fortis BC, who had been interested in supporting the city to expand our existing Building Better programming and look at building emissions more holistically. So this agreement was finished up early this year, and essentially the project began in late April. The news about the project was soon published, and you guys might have seen the brief that was completed back in May. And soon after this, Castlegar actually reached out to us to use some of their leftover grant funds they had from Fortis, and we agreed to a partnership. So the project expanded, and that brings us really to where we are now. Next slide. So overall, the project sought to A, collect local data on the average amount of embodied carbon associated with new builds in Nelson and Castlegar. B, engage with and offer education to key stakeholders. That's where we are now. And C, create a materials guide to give the building community guidance on how to take immediate action to reduce emissions in our building sector. And that's where we're moving towards. So now for the findings, Chris Magwood, a renowned green building and embodied carbon specialist with a background as a builder and contractor, will be presenting the findings. He's the current director of Builders for Climate Action, a leading force in the embodied carbon field. And we're so lucky to have him and his excellent team help our reaching out on the topic. And now I will pass things over to you, Chris.
Great. Thank you, Natalie. And thanks everybody for taking the time to join us this morning. As Natalie said, we are sort of unabashed nerds in this field, and there's a lot to sort of understand and then to cover here. So I am going to be putting a lot in front of you fairly quickly, but hopefully we can handle all the questions you have at the end. We'll try to leave a generous amount of time for those questions. So this is going to sort of be broken down into 4 parts. One is just looking at the topic itself. What do we mean by embodied carbon emissions, and how do we actually calculate it? So a bit of background on that. And then the bulk of the time on what did we actually find in the houses that we looked at in Nelson and Castlegar. And then a look at sort of some of the most impactful materials and some of the most helpful materials. And then, like I said, a good amount of time for some discussion at the end. So the sort of motivation for our organization to be doing this work is, like so many people who are concerned about the climate, sort of understanding that our global carbon budget is pretty limited, and the time that we have to act on this is short, and that a part of this is just understanding where are emissions coming from, and then what can we do about them. Whoops. So there are sort of two things that lead to exploring the emissions that come from materials. And one is kind of the understanding that for a long time in this space, we've been pursuing sort of energy efficiency and thinking about energy use as the guiding metric for buildings. So, this bar is kind of representing a typical Canadian home that might use 100 gigajoules, or in electricity, 27,000 kilowatt hours of energy. And the drive has been to make those energy numbers go down. And, collectively, the industry's actually done a really great job of doing that through better insulation, better design, all kinds of efforts that, everybody on this call has been putting in to make that happen. But what we have to think about when it comes to the climate is that energy use is not the same as greenhouse gas emissions. And that in fact, if that 100 gigajoule house happens to be using a really clean source of energy, its actual emissions footprint might be quite low. And if the sort of better performing house using less energy is using, say, coal-fired power, that its emissions may be higher than the building that's using more energy but is using cleaner energy. So first of all, there's sort of this understanding that we have to be focusing on emissions and not just energy. And then beyond that, there are emissions that happen not during the operation of the building. There's a whole bunch of emissions that kind of happen off-site, and that's what we're focusing on today, is what we're calling material carbon emissions, or you'll see me use the term MCE sometimes for that. And that is the emissions that happen because of processes in the sort of harvesting, transportation, and manufacturing of building materials. And for a long time, our focus has been just on that house and what happens when we move in and start using it. But this is sort of meant to sort of widen that discussion and say, oh, how we make the building has a large impact on the climate as well. So I was involved in a few early studies on this, looking at kind of archetype houses in Canada. Some other groups did the same thing in the US. And those studies of model homes kind of showed that an average of about 250 kilograms of emissions per square meter of floor area seemed to be about a reliable average for the impact of materials in home building. And that number, it might be sort of hard to put that number into perspective, but what that means in the Canadian context is that building materials for residential buildings may be the equivalent of about 14 million tons of emissions per year. And so in context, that's the emissions from over 3 million cars being driven per year, or from 3.5 coal plants. So it's not an insubstantial amount of emissions. It actually adds up nationally to be quite large when we work from model homes. A little bit about how we arrive at those figures. The methodology that we use in this study and in our work in general is to use documents called environmental product declarations, or EPDs. And this is an international standards organization, ISO, sort of standardized way of companies or industry associations being able to report on their emissions. It sets up kind of the rules for where you sort of make the boundaries around emissions that a product might be responsible for, and then rules around how you go about calculating and reporting those. And an EPD has a bunch of different environmental impacts that it considers, but the one that we focus on in this work is the global warming potential. And what that is it's an accounting of all the emissions that a material is responsible for, from the moment the raw materials are harvested to the time that the material is ready to leave the factory gate. And whether those emissions happen to be CO2 or methane or any other greenhouse gas, the number is sort of made into what's called CO2e, or carbon dioxide equivalent, so that we understand the impact on the climate in one metric, as though it was all carbon dioxide. So, throughout the talk, I'm going to be sort of using the word CO2e, carbon, as a stand-in for greenhouse gases, but really we're accounting for all the greenhouse gases that are emitted in making the material. All of that information has been put into a tool that we helped develop with Natural Resource Canada, and they call it the Material Carbon Emissions Estimator. And it essentially puts all that EPD data together, allows you to kind of take the metrics for your building, the areas, the R values, all the sort of key details of the building, and then associate the materials that go into that building and come up with the sort of material emissions for a particular house. And what that looks like, I'll sort of just quickly show you kind of like how one of these models gets built. But we know the size of the building, we know the shape of the building, we know the performance level of the building. And so essentially, we do a material takeoff, and then we take that quantity of materials, multiply it by the global warming potential from that environmental product declaration. And, component by component in the building, we're able to say, okay, this particular building using these particular materials has a carbon footprint, in this case of 212 tons. And so we're able to kind of see where do the bulk of those emissions live, which materials are high and low compared to each other, and then also look at what happens if that building, the same building, was made with different materials. And so next to that 212 kilogram emission, we modeled the same building with a different set of materials, and we got the carbon footprint of that model building down to 68 tons. And also we looked at using materials that store carbon in them, and we saw that you could actually get the same building to the point where it now no longer has a net carbon footprint, and is actually storing carbon rather than emitting carbon. So what all the early studies indicated was that the material choices we make in a building, have this huge range from, incredibly high, where there's no chance that we fix climate change if we keep making buildings in this way, to the possibility for buildings that not only aren't as bad for the climate, but actually maybe even do some good for the climate by drawing carbon down. And I'll just want to explain that notion of carbon storage a little bit, because it definitely took me a while to wrap my head around it, and I think it helps to sort of think it through. So when we're talking about carbon storage in buildings, it can happen one of two ways. It can happen through mineral carbonization of materials, so materials where carbon dioxide is drawn out of the atmosphere and turned into mineral form. There aren't really any of those on the market now. So what we're talking about in this study are plant-based materials. So anything that grows and is then turned into a building product, while it's growing, it's pulling CO2 out of the atmosphere. And around the planet, it's actually hundreds of billions of tons of CO2 is drawn down this way by plants. And then we can take some of those plants, instead of that plant matter going directly back to the atmosphere and becoming CO2 in the atmosphere again when those plants rot or burn or are eaten and digested. We interrupt that process by putting them in a building, and we take them out of circulation for the length of time that building exists, whether it's a few decades or a few hundred years. We kind of interrupt that carbon cycle and are able to sort of make a net drawdown of carbon from the atmosphere. And you may be wondering why I used a picture of a pretty plain looking apartment building as that example. And I use this because it's actually probably the world's largest carbon storing building right now. It's a mass timber structure made with prefabricated straw bale panels into a 7-story, 26-unit, 35,000 square foot apartment building in France. So, the ability to sort of really reverse the way we think about the climate impact of buildings is there. And so, that's the part of the lens that we're bringing to this study. There is a whole category of plant-based materials in terms of forestry products, timber products, that in this study we are not counting as having carbon storage, not because trees don't draw carbon down and store it, but because forests themselves are such important carbon sinks on the planet. And there isn't any clear and applicable methodology that we can find right now that determines the actual climate value of using wood in buildings. And what we don't want to end up happening is claiming lots of carbon storage in wood and ending up making our forests smaller while making the amount of wood buildings bigger. That doesn't really necessarily help the climate. So until such time as there is a way to calculate that, and there are lots of really great people working on this now, carbon storage in wood is not part of this study. So when you're seeing the results, any timber products that we're accounting for their emissions, but not storage. So with all that as kind of the background as to what we're counting, why we're counting it, and sort of how we count it, what did we actually find in Nelson and Castlegar? So we looked at 35 homes that have been built over the last couple of years. The data came from 3 West and the energy models that they had already done for these buildings. So Michelle, who's on the call, built these embodied carbon models in the Enercan tool. And what we found was that the average home of these 35 has about just over 26 tons of emissions associated with making the materials that go into that home. So, we had a range on either side of that, but across these 35 homes, that was our average result. And so if we take that average and expand it to the 72 new homes that were built between those 2 municipalities in 2020, that's about 1,900 tons of CO2, which is significant. I'm sure when the climate nerds in those municipalities add that up, they'll see that it's a pretty big chunk of the sort of carbon budget for those municipalities. And again, to put it in some perspective, every year the houses being built in the 2 municipalities are the equivalent of 465 cars being driven or 900 tons of coal being burnt. So, this is, even at that sort of average level, this is a pretty major impact in the municipalities from the construction of new homes. There we go. Sorry, my advanced button isn't working very well, so if I'm pausing oddly, that's why. I think I missed the last slide altogether. Yes, I did. So because 3 West had built energy models for these 35 homes, we were also able to see what the operational emissions for those buildings were as well, and get some sense of, how big is the material emissions when we compare it to the operational emissions. And again, the average across those 35 homes was just over 1.25 tons of emissions per year from the operations of the building. And so, you can see that there's a pretty big difference between the footprint of the materials and the footprint of operating the building, such that, if we use kind of all the average figures, it'll take 21 years of building operations before the operating footprint of the building even equals the material footprint of the building. And so, it's a significant percentage of the impact for that building moving forward. And from a climate point of view, it's also important to remember that really, these emissions, these 26 tons of emissions from an average house, they go in the atmosphere the day, somebody walks into the house. And so those emissions are in the atmosphere in full and continuing to sort of drive climate change over the life of the house. Whereas, these emissions accumulate more slowly. So really the impact of the materials is greater than just, where the 2 numbers intersect, because, these 26 tons of emissions are resident in the atmosphere for these whole 21 years, whereas these ones accumulate annually. So, it's a really, when you look at it this way, quite a large part of the overall impact on the climate from our homes. And if we look at the buildings in this study that were operating entirely on clean energy sources, the picture gets even more skewed in that it actually is 2115 before these material emissions equal the operating emissions from a building that is functioning on clean and or sort of renewable energy with a low emissions profile. So, this points to the fact that the better we make our buildings and the better the energy source gets, the more important this upfront materials part actually is, because we're not going to have the impact by just addressing energy efficiency. It's going to take us, over 100 years to have that impact that we could be addressing right now upfront with materials. So I want to introduce sort of one more way of looking at this number, because it's what allows us to look at different houses. So when we look at how many tons of emissions does a particular house have associated with it, obviously the size of that building is going to make a difference. A smaller house just has less materials than a bigger house. And so it's hard to kind of compare between different buildings. So in order to be able to compare, we use what's called a material carbon intensity. And that's like the total emissions divided by the habitable floor area of the building. And then we get a figure that's in kilograms of emissions per meter squared. And so for this study, these 35 houses had an average material carbon emission intensity of about 156 kilograms of CO2e per square meter. And one of the interesting things we found is that there isn't really a difference between the homes in Nelson and Castlegar, both in their sort of averages and their sort of high and low outliers. Construction practices between the two places seem to be fairly similar in terms of their climate impact. So that average kind of holds across both municipalities. And this just gives you a sense of the sort of the scale of that. So the blue bar here is that average. When we look at all 35 homes, they average out to 156. But the best home in the study was as low as 91, and the worst in the study was as high as 309. So, just as with the sort of model studies we did earlier, we can see that material choices make a really big difference in terms of looking at this on a home by home basis. And so across the study, what we found was when we looked at which materials ended up in the sort of top 10 most impactful across the entire study, what we found was that concrete in three forms, both in its use for footings and slabs, for foundation walls, and for garage foundations, occupies the number 1, 2, and 3 spots in terms of how often they turn up as in the top 10 of impactful materials. After that, we have windows, we have fiber cement siding, EPS foam, insulated concrete forms, vinyl flooring, steel siding, triple pane windows, and then hardwood flooring and drywall kind of tied in the 10th place. So again, this is averaged across all of the buildings. There are some materials that within a particular building, in particular things like XPS foam and certain types of SIP panels, were actually the highest impact materials in their specific building, but because not very many buildings use them, they don't show up here. So yeah, I think, in the discussion of, which are the high impact materials, there's sort of more to dig into than just this result. But what we clearly take from these results, and it maps closely to the other work we've done, is that these three categories of materials tend to own the lion's share of emissions for most homes. So that would be concrete, insulation in all its forms. When you look at sort of the total of roof, wall, and foundation and slab insulation, and then exterior cladding. So if we're going to spend time and effort really trying to figure out how to reduce material emissions, these are the places where we're going to get the biggest results from addressing. So we'll just look at each of them fairly quickly and talk about both what we can do now and what we might be able to do in the near future to address this. And with concrete, the sort of easiest strategy is to simply reduce how much we use. So that may be, doing less below grade work. That may be having less or thinner concrete slabs. There's all kinds of ways that good building design could literally reduce the amount of concrete. So that's a really straightforward way. There are also ways to address these emissions by ordering better concrete. So the simplest way to do that is to get concrete that has a higher percentage of supplementary cementitious materials, things like fly ash, blast furnace slag, calcined clay. There's a number of additives that reduce the amount of Portland cement in the concrete and therefore lower its carbon footprint without changing its structural properties. There's also Portland limestone cement and LC3 cement. Both have been on the market for a while now and are starting to sort of become more widely available. And similar to the SCMs, by reducing the share of Portland cement in the concrete, they reduce the carbon footprint of that. And there are also places now that directly inject CO2 into the concrete so that it's reducing the carbon footprint by kind of adding some negative emissions to the concrete by literally storing carbon in the concrete. So those are all things that locally you can start to discuss with your suppliers. How can they provide you with concrete that has a lower carbon footprint? Waiting for the next slide to come up. This is sorry about that. I'm not sure why it's taking so long. There we go. I talked earlier on about environmental product declarations. And one of the interesting things that we see when we look at EPDs for concrete is that the sort of range of possible outcomes from concrete are really, really wide. So the best EPD for residential strength concrete right now comes from a company in British Columbia, actually. And it only has 136 kilograms of emissions per cubic meter of concrete. The Canadian average, which is what we used in this study, is 369 kilograms per cubic meter, and a good 20% of the EPDs on the market are over 650 kilograms per meter cube. So it's the same material, it's going to do the same thing in the building, but its climate impact can be really different. And these differences come from things like different amounts of SCMs, different types of cement, and the possible injection of CO2 into that concrete. So what that practically translates to is that 1,000 square feet of an 8-inch concrete wall, if you're able to access the best concrete, it's going to have 2.5 tons of emissions, and if you're using the worst concrete, it's going to have 12 tons of emissions. So there's not even a design change required. It's just making sure that you're getting the best concrete possible, and you can make a 10-ton difference simply from ordering the material and being able to verify it with an EPD. And if you are talking to your concrete producer, there are a couple of companies now that offer really quick and easy ways to make instant online EPDs. So the sort of barrier to entry of getting an EPD, especially in the concrete market, is pretty low. So, that's something that you can discuss with your supplier, because really knowing where you fit in this range will drastically change the outcome of the carbon footprint of your building. And things that are coming that will make it easy to address this in the future, or easier, are things like biological concrete. So biolith is a concrete that is grown by feeding microbes in a bed of sand, and algae concrete is carbonate minerals that come from algae growth. So those are both under development right now. You can actually buy biomason tiles and bricks, but they're working on their ready mix now. So these things will actually completely reverse the impact of concrete and turn it from being the highest source of emissions to likely being the highest source of carbon storage in a building. So that's an exciting development. And so is the creation of recycled carbon aggregate. So the vast volume of concrete is aggregate, but the big part of the emissions is the cement that actually binds it together. But both of these companies are now producing concrete aggregates from recycled CO2. So they're taking emissions from either cement factories or power plants and recarbonizing that CO2 and turning it into aggregate. And again, the possibility there is that our concrete becomes a major source of carbon storage rather than a major source of carbon emissions. For insulation, again, if we're looking for the sort of straightforward strategies, it's using environmental product declarations to pick the best material from a particular category. So if you look at the Enercan tool, you'll see that, if you're looking at a material like fiberglass insulation, that, one manufacturer's carbon footprint might be double the one of another manufacturer, even though the product looks the same, costs the same, performs the same. By sort of choosing well within a category, you can make a pretty big difference. You can also start to switch out materials, picking an entire type of material that has a lower carbon footprint, or making a shift to choosing insulation materials that are actually carbon storing. And it's in this field of insulation that the sort of options for being able to store carbon in the building are really there right now. And in this study, in the 35 houses we looked at, 17 of those 35 used cellulose. So about half the homes had cellulose insulation in them somewhere. And on average, those houses put 2.35 tons of cellulose in those houses, which meant that overall 40 tons of CO2 is now stored in those 17 homes. And that literally means that the cellulose in those 17 homes eliminates the carbon footprint of 2 of the homes in the study. So, this was the sort of, I was going to say main carbon storage strategy, but really the only carbon storing material that we saw in the study. But even in the sort of limited way that it was being used, it's making a really big difference. And there is cellulose as a carbon storing insulation option. There is now both a Canadian and a US company making hemp fiber, which is a carbon storing insulation. Wood fiber products in terms of both board, bat, and loose insulation exists. Straw insulation exists, things that I don't have on the list, but they're things like cork and all kinds of other carbon storing insulation options that are sort of worthy of exploring if we want to start kind of reversing the impact of the carbon footprint in the buildings. And finally, the cladding category. This is a look at the cladding options, looking at 1,000 square feet of different kinds of cladding from the Enercan tool. And again, kind of seeing that depending on what you pick, there's everything from incredibly high carbon footprint to extremely low and every stop along the way. And so, being able to sort of think about those choices and what impact they have on the carbon footprint of your building makes a big difference too. And again, things coming down the pipe that will sort of help with this. Really great corrugated hemp panel that's now produced in the UK. Waste rice hulls are being used by a company in the US to make a cladding. There are companies blending lime and cork to make an exterior render or plaster. And things like heat-treated wood allow wood with a low carbon footprint to be used and be more durable. So these are just some of the things that could drive change and innovation on the cladding side. Now I know, because I'm a builder too, that what all of this costs is always a big question. And when we did our study for NRCan, the interesting thing we found is that there was no real correlation between material costs and material carbon emissions. In other words, sometimes the material with the highest carbon footprint also costs the most. Sometimes the one with the lowest carbon footprint costs the less, or the opposite could be true. There was sort of no direct correlation between cost, which means, for builders attempting to lower the carbon footprint of the building, that there is a bunch of low-hanging fruit out there in terms of, very affordable materials that can be substituted. And then there are, other things that are going to cost more, and you're going to end up sort of paying to reduce the carbon footprint. But I think, mostly what we found is that there are some pretty cost-effective ways to make really big impacts on the overall carbon footprint of the building. Another interesting result from the study, and this is something that I didn't really think about or anticipate in advance, but it makes sense now that we've looked at it, is when you add a garage to a building, and 12 of the houses in the study had garages that we could look at the calculations. They were sort of separate from the main home in the calculator tool. That those 12 garages had a total of 78 tons of emissions associated with them, and that they averaged 20% of the emissions from the house that they were attached to. So clearly, the way that making building space for cars contributes a lot to the overall climate impact of the home in general. Another thing that we did once we had completed the study was we took the calculator results for the home that had the highest carbon footprint in the study, so the one that had 309 kilograms per square meter, and we just made some really simple material substitutions. We changed the concrete mix from the Canadian average to not the best one possible, but a quite achievable one. We changed the foam ICFs to wood chip ICFs. We changed the wall insulation from mineral wool to cellulose, the XPS insulation on the outside of the building to wood fiberboard, the hardwood floors to being half hardwood, half linoleum, and the roof insulation from mineral wool to cellulose. And just those 6 changes halved the carbon footprint of that building. It got it from being the highest one in the study to being basically bang on the average. So not that we're saying this is what you should do with a house, but just sort of trying to make the point that there are some pretty straightforward and simple interventions. There's only 6 changes here, but that made that building significantly, it halved its carbon footprint. And then we kind of moved forward with that, and we looked at other switches we could make, like changing the sub-slab insulation to foam glass, going for the best possible concrete, going to a treated wood foundation so there was no concrete involved, changing the wall insulation to straw bale, changing all the flooring to linoleum and cork, and changing the roof insulation to cellulose. Now that same house is down to only 55 kilograms per square meter. So, only a third of the average, and a huge reduction from the original 309. And again, these aren't prescriptions that we're making. This is just sort of showing the power of material substitutions to really drive changes in the carbon footprint. And I'm just about done. And to sort of bring this all home right to your area, we did look at one house that 3 West kind of pointed out to us that's being built in the area. It's a laneway house by Pacific West Builders. And if we sort of look at the average building in the area, this one has only 2 kilograms of CO2e per meter squared associated with it. So this is essentially not just a net zero energy building, this is a net zero material carbon footprint building. And the main changes that contributed to that here was not having a concrete foundation at all, but moving to helical piers, not having any foam insulation under the slab because it's raised. They were able to use cellulose in the floor, cellulose in the walls, wood cladding, and cellulose roof insulation. Those steps alone kind of drove this building to be essentially a net zero building from a material carbon footprint perspective. So a great example showing that, this can be done. It's not pie in the sky kind of thinking, and that, there are builders right in the region who are already approaching this kind of zero carbon footprint home in their practice already. So I'm just going to quickly summarize, and then we can get into some discussion. The big takeaway is that reductions in material carbon emissions can be the equivalent of decades worth of operational reductions. I think that really stands out. But what I really want to make clear is that this isn't an either or scenario. We're not suggesting that we sacrifice energy efficiency for material efficiency. We really need to be doing both. I mean, if we're going to meet the kind of zero carbon by 2050 targets that are going to be necessary to prevent runaway climate change, we have to be doing both of these things. We have to be making really energy efficient buildings with really clean energy sources with really great materials. That's what's going to get us to an actual net zero. And that we don't have to sacrifice efficiency to make buildings with a really low upfront carbon footprint. The little laneway house we showed you also had one of the lowest operational carbon footprints of the entire study. So these two things go together. Like I said, garages have a major impact. That's definitely something that you would want to be thinking about. That a small proportion of materials, that concrete, insulation, and cladding, make up the biggest proportion of the material impact. So really, putting your efforts into reductions in these areas are going to get the biggest results. That the use of carbon storing materials can help offset the overall emissions and get a building close to or even sometimes below net zero. That there are a bunch of options out there that you could start to implement right now, and that we're all going to have to think about how to seek out and adopt new products that do even better from a carbon footprint stance moving forward. So with that, I want to sort of thank you for your listening time, and now open up the floor to discussions. I'm not seeing the questions, but I am seeing there's more than 30 things in the chat. So Natalie, I guess we've got some talking to do.
Thanks, Chris. Yeah, there's been some great discussion in the chat. I'm going to start off with Greg's question. So he has one about, is there a model available that can compare the carbon impact, household insulation, and capital costs of various material input scenarios? I think part of it is answered later on the presentation. This was asked at the start, but I just thought I'd give you an opportunity to answer that, Chris.
Sure. Yeah, I mean, I think that is something that is doable, but we looked at building costing right into the NRCan tool for looking at carbon footprint, but it's so complex, to try to do that for different regions of the country. Different materials cost more or less depending on where you are. The labor scenario can be really different. So, really, I think the best way to approach it is, you as the builders in the community, what things cost. So that NRCan calculator can provide you with the carbon numbers, and then you can attach your own costing numbers to those. But in my own practice here, what we found is that there are a handful of things we can do that cost either the same or sometimes even a bit less, that make a huge difference, and those are sort of the no-brainers. And then we start cherry picking. We start actually looking at, do we spend a bit more on this material to bring the carbon footprint down by this much? That just becomes, the kind of internal discussion. The same way you'd think about, do I go for double or triple pane windows? Do I go for, this countertop or that countertop? There's always sort of a value to results kind of trade-off that we're considering. And I would just sort of suggest that, once this is on your radar, this just becomes one more of those things that you put on the table to weigh up with your clients.
Thanks, Chris. I'm going to jump over to a verbal question. Derek has his hand up.
Hi there, thanks. Really great presentation, very enlightening. You made a very compelling case that we can't really ignore this. My question is around what you see as the municipal path forward to addressing this, because basically none of the emissions that you've mentioned are actually counted in our inventories. So it's, we've got a bear of a job with the emissions we already count. And so, yeah, what sort of thoughts do you have on what our role as in municipal governments have to deal with this?
Well, I mean, I'm not entirely sure. I'm not, I think the thing that the municipalities can do, and municipalities have done such a great job across the country in doing this, is, encourage the leaders in both energy efficiency and climate reduction. Encourage them to do the most that they can do. Kind of use your ability to encourage people to set really good examples. So, there's a small municipality here in Ontario, Duro-Dummer, and they have a program where you get your building permit fees back if you can make a house that's under 75 kilograms of emissions per square meter. So those kinds of incentives, I think, really help. I know that these emissions aren't yours, but the buildings are being built on your in your territory, and I think you don't really, without changing the actual building codes, don't have any way to directly regulate it. But I certainly think that there's ways to encourage excellence and make sure that there are really great examples in your municipality, that people understand what's been achieved when that example building is built, and sort of really help drive the market that way by kind of trumpeting the leaders and making sure that the people in your municipality know that, hey, if I'm going to build a new home or seriously retrofit a home, I could be having no carbon footprint. I think to a large degree nobody's aware of that, and so those kinds of programs that push the innovation and highlight what's achievable is probably the most impactful role.
Thank you.
Yeah, thank you.
So we'll go on to the next one from the chat. That is from Ray. So he's asking about, regarding not including carbon storage of wood, would this still apply for log homes using round logs as the walls?
Yeah, I think the topic of wood is really complex. I think there probably are wood products on the market right now where we really could be counting them as carbon storage. I think there are some forests that are sort of using exemplary forestry techniques, and that the carbon storage of the forest can be grown while taking trees out, and that's when we can start counting the carbon in wood. If the overall carbon stocks in the forest are increasing while we harvest our wood, and there are lots of people demonstrating that that's possible, then we should be counting that wood as carbon storing. But then the exact opposite can happen. We can be taking out wood and dramatically worsening the climate by doing that. So I would say the logs for a log home, in the same way, it depends where did they come from. They'll have a little bit less carbon footprint in that no energy was expended in milling them and kiln drawing them and that sort of thing. But if they come from a massive clear cut where that carbon is going to take centuries to rebuild, and all the carbon that was stored in the soil was lost to the atmosphere, that log home is not helping. But if they were selectively harvested and come from a forest, stocks are growing, and it's probably a great doing. We just don't have any way of clearly saying, yes, this wood is good and is carbon storing, and this wood is not. I feel like we'll start to see that in the next couple of years, but for now, I would say, for us in our own practice, it's a gut check. Like, we get most of our wood from local mills here in Ontario. I can go visit the stands where they're being harvested. They're being harvested by families who've managed those woodlots for 100 plus years. I feel very confident that that wood is really good and probably is having a net carbon storage. But when I go to a big box store and just pull a 2x4 off the shelf and I have no idea where that's coming from, I don't think we can just assume that we're doing the right thing or achieving carbon storage by doing that.
Natalie, can I just do a little bit of background with this?
Absolutely. Go ahead, Ray.
Yeah, I'm an energy advisor, a long time energy advisor, 100% behind what you're doing here. And I've had chats with Michelle, and we've had emails and phone calls between each other and everything. I got into the logs 4 or 5 years ago, I suppose. I did a presentation to the BC Log and Timber Building Association, mainly on step code. And then it very soon became clear, like, step code's going to kill the industry if something doesn't come up. So they're sort of pinning their hopes, and they're looking at other, not just your calculator, looking at the Athena one and trying to get some form of embodied carbon into the building code. I'm kind of piggy in the middle because I understand the step code and how that works and what it's supposed to achieve. I understand this too. And it's, it's trying to temper the log builders down because they see themselves as like poster child for this type of thing. And I can understand that too. So it's kind of difficult. BC standards have told me several times that they're not actually going to tank the industry, which would be a disaster. And politically, I don't think that would be allowed to happen either. But it's just a matter of getting something built in somewhere to help these guys out, The other thing I've seen with a lot of, there was a comment on one of my comments, yeah, you can do wood and cellulose. Yeah, that's fine. You haven't got a log home anymore, have you? And, there's a market for them, and a good market for them. And there's loads of jobs and all the other spin-offs, that's just really the background behind it.
Yeah.
Playing devil's advocate, really.
Yeah, no, and actually I don't even see it as devil's advocate. I think those are really good points. And, by being, like you said, sort of, piggy in the middle, I feel like I'm sort of that person as well. And we just did a study for Enercan. You can sort of download the report. But one of the things that we sort of propose in that report is that we stop thinking about energy and material emissions as two different things that sometimes are in competition, and we put them together and we say, what's the carbon use intensity of this building? Like, when you add its materials to its operation, what do you get? And I think that's a path for log homes where it's like, yep, maybe you're not as energy efficient, but if you're using a relatively clean energy source and the overall carbon footprint of your building is really low, then as a whole, that building is responsible for a reasonable amount of emissions versus, we can see from this study that we can make an incredibly energy efficient building that has a huge carbon footprint attached to its materials, which would actually be worse for the climate than the slightly underperforming log home, but with a lower material footprint. So I think, we need to start thinking about that metric as, like, you put both of these things together, and that way there's more than one path to get there. Maybe, extreme energy efficiency isn't the right path. Maybe it's materials in a place where you only have, less or more carbon intensive energy available to you, then you have to think about materials or energy efficiency. Like, we sort of open up multiple ways to get to a low carbon building when we put, energy use and material use together.
Yeah, no, I totally agree with that. And that's the problem I'm finding, is that one side wants this and the other side wants that. And you really, they should be together, as a one-off, when it comes to.
Yeah, and I think what we really want is a climate that's, habitable. And so, for me, that's sort of that's the trump. If there's 4 different ways to get there, let's just get there in, the best way for a particular builder in a particular area. But let's make sure that it's, it's serving the climate and not just a sort of arbitrary measure.
Oh yeah, no, totally agree. So I think the sooner all this comes into play, the better, really.
So I'm just going to jump in here. Thanks you guys for having such a great back and forth on that. I'm going to go over to Sarah Maleska's question. We don't want addressing embodied carbon to exacerbate the housing crisis. She prefaced this with a bit of a devil's advocate position here. So wouldn't advocating for less basements negatively impact the amount of rental units available by potentially having less basement suites? There was a little bit of conversation just about how zoning and NIMBYism played into this, but I wanted to open this up to you to speak to it, Chris.
Sure, and I think I would go, my go-to would be to go straight to that. Like some of that are things that can be handled by zoning. If you could build a 3-story house without going into the ground, you wouldn't be eliminating that space. You would just have 3 above ground instead of 1 below and 2 above, or whatever the scenario is. So there's that. I think there is a way to make basements with a lot lower carbon footprint. Like in no way is this study saying to you, don't ever make a basement, but it is saying, think about the materials in your basement. If you can, get a really low carbon concrete, do that. There are insulations that you can use in that basement that have a massive impact on the carbon footprint. So going with the better versions of that. Treated wood foundations show up really well in the study. And so, there's a way to make a basement in that way. There are some innovative ICF products out there that have a much lower carbon footprint. So this is not at all saying don't make basements, but what it's flagging is for houses that have basements, a pretty large chunk of the emissions live in that space. So there's multiple ways you can address that. One of which is don't build down there, but the other of which is build down there, but be more judicious in the kinds of materials you choose to do that.
Thanks, Chris. Closing in on the end of the hour, I just wanted to get in one final question. Greg Dong, he asked, I wonder how many existing homes replace insulation as part of retrofits each year versus new builds. I thought that we could speak maybe a little briefly to why we didn't incorporate in the study or why we couldn't, and what work is to come on this feature.
Yeah, I think that's an amazing point. The federal government has identified retrofitting homes as a huge part of its climate action plan. And so, what's interesting with renovations is that it in some ways it even exaggerates the sort of difference between operational emissions and material emissions even more than with new construction, because you can put a lot of really high emitting insulation into a building and only achieve a relatively small amount of operational emission reduction for doing that. And so that balance becomes even more important to understand. That the carbon use intensity that I was talking about with Ray, that metric I think becomes really important for retrofits, because you want to make sure we can't afford to invest 40 tons of emissions onto an old home that even still is going to have 10 tons of emissions a year associated with it. Maybe we brought it down from 12 to 10 or from 15 to 10, which is great. But if we did that at a cost to the climate of another 40 tons of emissions, it's not helping. So I think in the retrofit space, thinking about the sort of how those two things blend, the carbon footprint of your materials and then what you achieve on the operational side, we have to think about those together. Or we could be doing literally, the federal government may end up paying people to make the climate worse, as part of their plan to try to make the climate better. And so I think we have to be really cautious moving forward. And I think, Natalie, part of the output of what we're doing with you is going to look at renovations and renovation materials, even though it's not part of the study that we did on these new homes.
Yeah, absolutely. Perfect timing there, Chris.
Oh, yeah, 12 o'clock.
Exactly. Well, thank you all for coming. I'll be sending a follow-up email with the slides, hopefully, and eventually with a recording of the presentation. I'll give also a post-presentation survey in case folks in the RDCK want to stay involved. We're going to be doing some workshopping next month. Please, as I've said many times in the emails, if you have any questions, please reach out to me. I love to get them. I'm very passionate about the topic, and the whole team is really interested in hearing feedback. So thanks again, everyone, and have a good day.
Thank you, everybody.